Okay, now that we've done a little bit of work with moving a function around with transformations, I'd like to go back to page 30 of your notes and go over a topic that's pretty easy to understand. It's not too difficult. It's about increasing and decreasing functions and behavior. So first of all, I would like to use this graph right here in the middle of page 30 to explain some of this information that we're going to talk about today. Right in here we have an explanation of what increasing is, decreasing, constant, etc. And you can read that for yourself. There's also a definition for relative minimum and relative maximum. And I'm going to talk about all of these things, but I want to use this graph right here. So what I'm going to do is I'm going to expand this graph right here, make it a little bit bigger, and then we're just going to talk about this graph with using all of these different terms. So if you need to stop the video at any point and reread the definitions, go ahead and do that, and then you can go back to the graph. Okay, I'm going to go ahead and expand this graph. Okay, so one of the things we're going to talk about is end behavior of a graph. This is a typical polynomial graph. The end behaviors on this particular graph are what we call falling left. In other words, on the left side of the graph right here, the graph is going down to negative infinity. It's also going to the left to negative infinity. So we would say that this graph is falling left. Now if this graph was going in the opposite direction, say right here on the graph, say it didn't bend back down, say it went back up this way. This graph would then be called, the end behavior right here would be called rising left. Rising left. That would be its end behavior if that were to happen. Now if we look over here to the right side of the graph, we see that this particular graph over here on the right is going up on the right. We would call that rising right. But say that graph didn't turn and go up right. Say it kept going down. Say, for example, if this graph kept going down this way and it was going down this direction and our x values were positive but our y values were negative, we would call this particular end behavior falling right. Falling right. And that's pretty much it for end behavior. That's all there is to it. Okay, so let's go ahead and look at another aspect of our graph called the maximum and minimum, or maxima and minima of our graph. We have two different kinds. We have absolute maxima and minima, and we have relative maxima and minima. And there's that's two different kinds of minima and maxima. So we need to determine, define which one's which. Okay, this particular graph doesn't have an absolute maximum or an absolute minimum because our end behaviors go down to infinity on both ends, down to infinity on the left and up to infinity on the right. So this one doesn't have any absolute maximum or minimum, but it does have some relative maximum and minimum points, and I'm going to point out those to you right now. Okay, so right here, if we're looking at the graph between the values of, say, -4 and -3, between -4 and -3 for the values for x in this particular domain, so we would write it like this, -4 comma comma, -3. Close brackets. If I'm looking in between these two particular values for x within this part of the domain, I want to look to see where is the maximum point on my graph. So I come up here and it's about right here. So I'm going to put a dot there and I'm going to label that point. It's about, I'm going to say it's about -3.5, 1, 2, 3, 4, 5, -3.55. So that particular point right there, which is -3.55, would be our relative maximum between the values of -4 and -3 for x. But what if we wanted to look at the entire graph? Let's look at the graph as a whole. Now if I want to look between the two endpoints, between -infinity and +infinity, so I'm looking at the entire graph, I want to look at the relative maximum and minimum points between these two values. Okay, so the relative maximum point is going to be the highest point relative to this particular domain, and so in this case our relative maximum would be right up here, the same point we had before. Our relative minimum would be the lowest point where it bends, which would be down here between those two values of -infinity to +infinity. If I change my domain to say between -4 and say 1, okay, between -4 and 1, -4, 1, and between this interval right here, my relative maximum and minimum will change. Now my relative maximum is still this point here, but my relative minimum point for this particular interval of the domain is right here. So you need to pay attention to what interval you're given, because that matters when we're looking at relative maximum and minimums. Absolute maximum and minimums are different. Absolute maximum and minimum is the absolute highest point. So if I were looking at the absolute maximum point for this graph, it would be none, because this goes on to infinity. And if I were looking for the absolute minimum point for this graph, it would be none, because it goes negative all the way to infinity. So on some graphs we stop and we have endpoints. So those endpoints might be maximum or minimums. So it depends on the graph you get, and when we go over some of these in class, you'll see how that works. We will practice in class together. Okay, let's go on to the next set of notes. Okay, so here on page 34, we're looking at this particular graph. So go ahead and turn to page 34 of your notes. I'm going to go ahead and expand this so that the graph is a little bit bigger so you can see it. And we're going to answer questions 9 through 12 about this graph. So let me expand the graph so you can see it, and then we'll answer the questions. Okay, so here's the graph. The first question is, let's see, find the coordinates, if any, where the above has an absolute maximum value. Okay, so we just talked about that, and we said an absolute maximum value is the highest value of the graph, if there is one. Well, this particular graph doesn't have an absolute maximum value because both of these ends go to positive infinity. So because both ends go to positive infinity, we do not have an absolute maximum value. So now we're going to see what the next question says. Well, let's see. The next question says, state the intervals where the above is increasing, decreasing, and constant. Okay, well, what does that mean? All right, well, when we are talking about increasing and decreasing, we're talking about what is happening to the value for y as we look at the graph from left to right. So as we look at the graph from left to right, what is going on with the value for y? So from negative infinity all the way to this point right here, the graph is doing what? Even though there's an arrow pointing up here, what is the value for y doing between here and here? Well, it's decreasing, isn't it? Okay, so that value, that is a decreasing graph between negative infinity and negative 1.5. So then we say, okay, well, from negative 1.5 to this point right here, what is happening with the value for y? Well, between there and here, y is increasing. And we can just keep going through the graph that way from, I'll say, negative 0.5 to 0, decreasing, increasing, decreasing, increasing. Okay, so that's basically increasing and decreasing. So between these values, these are the values where the arrows are pointing down, those are decreasing, and where the arrows are pointing up, that's where your graph is increasing. So when we ask for increasing or decreasing values, that's what we're looking for between those intervals. So we're going to ask for the domain value. So what's the domain value for this decreasing? Well, this goes from negative infinity all the way to negative 1.5 in the domain. The graph is decreasing. From negative 1.5 to negative 0.5, the graph is increasing. From negative 0.5 to 0, the graph is decreasing again. And from 0 to, 0.75, the graph is increasing. From 0.75 to 1.5, it's decreasing, and so forth. So you have to look at the values for x as we look from left to right. What's going on with the y value? Is it going up or is it going down? Okay, so question 11 asks, what is the domain and range for this graph? Well, the domain is obviously from negative infinity to positive infinity. We already mentioned that. But the range is not negative infinity to positive infinity. We want to look at range from bottom to top. So we want to see how far down does this graph go? Well, it doesn't go any further than negative 6. You see this? So in other words, our range is going to start at negative 6, including negative 6, and it's going to go up to infinity. So the domain is negative infinity to infinity, and the range right here, range is negative 6 to infinity. And then it asks, question C, 11C asks, where is the graph discontinuous? Well, discontinuous means that we have a break in our graph. And obviously you can see from this graph that there's no break. So in other words, there's no asymptotes in this graph. We see a line, this goes to infinity, comes in, goes up and down, up and down, up and down, goes back up to infinity. There's no break. There's no place in my graph where I lift my pen. So I can follow this graph along, and I never lift my pen off the paper. And because of that, I can say that my graph is continuous. There are no places in my graph that are discontinuous in the portion that we see. And we don't see any breaks or any asymptotes or any holes in this graph at all. So we would have to say that this graph is continuous. And then lastly, question 12 asks, what are the absolute minimums? Well, this particular graph does have some absolute minimums, and we could actually say, well, they're right here. There's two absolute minimum points. And so we could actually list them both as absolute minimums because they're at the same y value. Since they're at the same y value, we can list them both. One of them's at negative 1.5, negative 6, and the other one's at 1.5, negative 6. And we could use both of those points as our absolute minimum points. Okay, let's go on to the next set of notes. All right, so now turn to page 52 of your notes. This will be the last section that we cover before you take your test on Thursday this week. This will be the last thing we cover. Combinations of functions. Now this is something that we did in Algebra 2, and I'm going to expand this out so you can see it better. This right here gives the different operations that we can do for combining functions. So here we have adding, subtracting, multiplying functions together, and dividing functions. So it says here in the notes that note that if f and g must have overlapping domains. Don't worry about that just yet until we start doing combinations. The only reason we would need to worry about that is if we were combining rational functions, or if we had a function that was a square root or something like that. We might have an issue with domain. But since we're working with all polynomials on this page, and x could be any value, we really don't have to worry about overlapping domains right now. We will have to worry about that later, though. Okay, so let's go ahead and do some of these problems. They're not that difficult. We're going to look at, first of all, our functions. We have use these functions below. So we have f of x equals 3x minus 4, g of x is 2x squared plus 5, h of x equals 8 minus 3x, and p of x equals x squared minus 2x. Well, what do all these letters mean? What does F, G, H, and P mean anyway? Well, they're just the name of the graph. You know, we could call this one Fred. Okay, this one we could call it George. This one over here, we could call that one Harriet. Okay, or Helen maybe. And this one right here we could call Paula. It's just the name of the graph. It doesn't really have anything to do with the calculation of the function itself. It's just the name of the function. So we're calling this one function P, function H, function G, etc. Okay, so the very first problem they give us here is, what is f of negative 3? Well, basically all we're doing here is we're taking our function f, which is this one. Okay, this is function f, and we're going to substitute a negative 3 everywhere there is an x, and we're going to evaluate that. All right, so let's go ahead and do that. So we take our 3, and inside where the x is, we're going to put our negative 3 and subtract 4. Well, 3 times negative 3 is negative 9, and negative 9 minus negative 9 minus 4 is negative 13. So f of negative 3 equals negative 13. And we could even write that as a point. We could write it like this. We could write negative 3 comma 13. We could write that as an ordered pair. All right, so when x is negative 3, y is 13. Or when x is negative 3, f of x is 13. So this right here is our ordered pair. We could actually plot that on a graph. All right, so that's all you do for 1 through, let's see, 1 through 8. And then if you wanted to see one like this is different. X plus 2, we're going to plug this whole thing into where x is in f of x. So let's use that f of x one more time, and now we're going to plug in x plus 2 and see what we get. Okay, so we've got 3, and then we're going to plug in our x plus 2, where the x was, and then we're going to subtract 4, and we're going to evaluate that. Well, let's see what happens. We get 3 times x is 3x, 3 times 2 is 6, minus 4. So at the end, when we finally combine like terms, we have 3x plus 2. That would be our combination. Okay, so on page 53, we have some more examples here. Here we have, we're going to combine function h plus function g. And what we're going to do is we're going to evaluate that when x equals 3. That's what that means. So right here we have the number 3. That's what we're going to plug in for x. And we're going to add h plus g together. All right, so there's a couple ways we can do this. We can go ahead and add h and g together first and then plug in 3. Or we can plug in 3 into h and plug 3 into g and then add them together. Either way it works just fine. They both work fine. So let's do the functions first. We're going to combine them. I'm going to do it one way first and then I'll do it the other way, and you can decide which way is easiest for you. All right, so let's just try this one right here. Okay, I'm going to expand this a little bit so that it's a little bit easier to see. Okay, so we have this function right here is h plus g of 3. All right, so function h is 8 minus 3x. Okay, 8 minus 3x plus g. What's g? G is 2x squared plus 5. 2x squared plus 5. And I'm going to add those two functions together. In other words, I'm just going to combine like terms. Well, the only terms I have here that are alike are the 8 and the 5. None of these terms have anything else in common, so I'm just going to rewrite this polynomial in polynomial order, which means the highest degree goes first. So that means my 2x squared is going to be written first. So 2x squared minus 3x plus 13. Now what I'm going to do is I'm going to substitute in this 3 they gave me, this 3 right here, for my x, everywhere there's an x. So I'm going to go ahead and plug it in. So right here, I put my 2, and I open my parentheses, I put my 3 in there, square it, I have another 3. Every time I substitute in a number, I use parentheses. I don't care if it's positive, negative, or whatever. If you're going to substitute a number in to a function, you need to use parentheses. If you don't use parentheses, you're going to get the wrong answer every time. So please, please, please use parentheses, especially if you're using a calculator. All right, so this number right here is 3 squared, which is 9. 9 times 2 is 18. And then I have 3 times 3, which is 9, plus 13. Gives me a total of 22. All right, let's try it again the other way. And then, you, like I said, you get to pick which way works best for you. We're going to go ahead and do it the other way. We're going to plug in the 3 into both functions and then add the two numbers together. Ready? Here we go. All right, we're going to choose the h function first. H of g is 8 minus 3x. And I'm going to plug a 3 in there. So 8 minus 3 times 3. This gives me an 8 minus 9, which is a negative 1. Then I'm going to do the g function. The g function is 2x squared plus 5. So 2 times 3 squared plus 5. That's 3 squared is 9. 9 times 2 is 18. 18 plus 5 is 23. And then I just combine these together. Negative 1 plus 23 is 22. So either way, I get 22 as my answer. So it doesn't really matter which way you want to do it. It's totally up to you. You can add them together first and then plug it in, or you can plug it in and then add them together. All right, so let's take a look at one where we're multiplying. So this says F times G. Same thing here. You can plug the 2 in first and then multiply the numbers together, or you can plug the number in and then into each function and then multiply that together. So let's try both ways. Okay, so here's the first way. We have function f, which is 3x minus 4. I'll write that one down. 3x minus 4 times g, which is 2x squared plus 5, and then we're going to plug in a 2. All right, so you can already see by this one that, that this is going to be a little more difficult. This one we have to FOIL. So we're going to FOIL this, first times first, outside times outside, inside times inside, last times last, then combine like terms. So we're going to do 3x times 2x squared. That's going to be 6x to the third. Then we're going to do outside times outside, which is 3x times 5, 15x. Then inside times inside, negative 4 times 2 is negative 8, x squared. And then last times last is negative 4 times 5, which is negative 20. Well, we can't combine any of these terms because none of them are alike. But I am going to rewrite it in polynomial order because I'm a math person like that, and I like to have my polynomials in order. So I'm rewriting my polynomial so that it's in order 3, 2, 1. 3, power 2, power 1, constant. Okay, so I write it in polynomial order, then I'm going to plug in my 2. So here we go. 6 times 2 to the third minus 8 times 2 squared plus 15 times 2 minus 20. Well, you can plug this in your calculator or you can do it in your head, whichever you like. I'm going to go ahead and work this out, get a total, and then we'll be done with this one. So after solving, I get the solution of 26. Okay, so let's do it the other way and see if we get the same answer. All right, so the other way we would do it is by entering our 2 into our functions first and then multiplying those two numbers together to see what we get. Okay, so let's try it this way. Let's go ahead and plug our 2 into x. 3 times 2 minus 4. And we're going to multiply that times 2x squared plus 5. Okay, so here we have 3 times 2, oops, I made a mistake there. 3 times 2 is 6 minus 4 is 2. And then 2 squared is 4 times 2 is 8 plus 5 is 13. And 2 times 13 is 26. So you can see that probably plugging your number into the functions first and then multiplying them together is a little bit easier than multiplying the functions together and then plugging in for 2. So it kind of depends what you're required to do for a particular problem. Sometimes you have to use a variable instead of a number. So sometimes it might be easier to go ahead and combine the functions together first before you plug anything in. It just kind of depends on what kind of problem you're working with. But if all you're plugging in is numbers or maybe one variable, you could probably do it this way and it would work fine. Number 14 is a little different. See if you can do that one on your own. That's all for now.